Hello everyone, welcome to the lecture series on kinematic analysis of mechanisms using analytical methods. Under this, we will discuss about analytical method for velocity and acceleration analysis of slider crank mechanism. In previous lecture, we have done the required derivations for the velocity and acceleration analysis of single slider crank chain. We have derived the equations for piston displacement, piston velocity, piston acceleration, angular velocity of connecting rod, and angular acceleration of connecting rod. This is the single slider crank chain having crank with length of R, connecting rod length of L. We'll assume that the crank is rotating in clockwise direction with angular velocity of omega radian per second, and the instantaneous displacement of crank from IDC is theta, and the corresponding displacement of connecting rod is phi. Stroke of the piston is S, which is equals to 2 times the crank length. The very first equation we have derived is sin phi equals to sin theta upon n, which is obtained from these two right angle triangles PC. Say this is point M. So from this first triangle we get sin of phi equals to Cm upon L, and from the second right angle triangle CMO we get sin of theta equals to Cm upon R. So common side is Cm. Equating for common side Cm, we obtain this relation between the crank and connecting rod displacement. Next relation is obliquity ratio, which is equals to n, and which is defined as the ratio of length of connecting rod to the length of crank. Next is the instantaneous displacement of a piston xp, which is equals to r 1 minus cos of theta plus r n minus under root of n square minus sin square theta. Using this equation we can find out the displacement of the piston at any instant of crank rotation. Number 3 is piston velocity Vp, which is equals to r into omega sine of theta plus sine twice theta upon twice n. Next equation is of piston acceleration. Fp is equals to r omega square cos of theta plus cos twice theta upon n plus r into alpha sine of theta plus sine twice theta upon twice n. This is obtained by differentiating the velocity equation. When we find out time derivative of this equation, Vp equals to r omega sine theta plus sine twice theta upon twice n, we get this acceleration equation. This acceleration equation consists of two components. We have seen this. The first component is called a centripetal component of acceleration, whose magnitude is equals to r omega square, and the second component is called as tangential component of acceleration, whose magnitude is equals to r into alpha. Next is the angular velocity of connecting rod. Omega pc is equals to crank speed omega into cos of theta divided by obliquity ratio n. When we differentiate this equation with respect to time, we get the equation for angular acceleration of connecting rod alpha pc, which is equals to minus omega square sine of theta upon n plus alpha cos of theta upon n, where omega is the crank speed and alpha is the acceleration of crank if it is rotating with non-uniform speed. So these are the equations which we'll use to solve the numericals. So let us take example number 1. So example number 1, a reciprocating engine has a crank of 60 millimeters long and the connecting rod is 240 mm long. It runs at 1200 rpm. We have to determine the acceleration of piston when crank is at 120 degrees past IDC. 120 degrees past IDC. We have to determine acceleration of piston. So first of all, let us note down the given data. So crank length is given as 60 millimeters. So crank length indicated by R is 60 millimeters. The connecting rod is 240 mm long, which is indicated by L. So L equals to 240 millimeters. Then from the values of L and R, we can determine obligatory ratio N, which is equals to L by R. So N equals to 240 divided by 60, which gives N equals to 4. So obligatory ratio is 4 by calculations. Now the speed is given in RPM. The engine runs at 1200 RPM. So we'll convert this speed into radian per second using this equation. Omega equals to 2 pi n upon 60. So putting the value of n, which is equals to 1200, we get omega is equals to 125 radian per second. So theta is the crank displacement, which is given as 120 degrees from IDC. We always take the displacement of crank theta from IDC with respect to IDC, and which is given as 120 degrees. So theta equals to 120 degrees with respect to IDC. Now we have to determine the acceleration of piston. The equation for the same is equals to r omega square cos of theta plus cos twice theta upon n. Out of this, we know r, which is 60 millimeters. We know omega, which is 125. We know theta, which is 120 degrees. And we have determined n, which is 4. So now we will substitute these values in this equation. So r is 0.06 meters, omega is 125 radian per second, theta is 120, and n is 4. Now after solving this equation, we get acceleration of piston as minus 592.141 meter per second square. That means the piston is retarding as indicated by the minus sign. Now question number 2. The stroke of the steam engine is 15 centimeters and the connecting rod is 30 centimeters in length. The crank rotates at 600 rpm. When the crank is made 45 degrees from IDC, the angular velocity of connecting rod is. Stroke of the steam engine is given as 15 centimeters. So stroke equals to 2 times the crank length. So from this we can determine the crank radius. Stroke is 15 centimeters, which is equals to 2 times the crank length. So crank length becomes 7.5 centimeters. And the connecting rod is 30 centimeters in length. So L equals to 30 centimeters. The speed of crank is 600 rpm. So first of all, we will find out the obligatory ratio L by R, which is equals to 30 divided by 7.5. So N is 4. Now the crank rotates at 600 rpm. So we'll convert this speed into radian per second. So omega equals to 2 pi n upon 60. So we get omega as 62.83 radian per second. Now the crank angle is 45 degrees from IDC. So we take theta is equals to 45 degrees. We have to determine angular velocity of connecting rod, which is given by this equation. Omega PC equals to omega cos of theta upon n. Now we know omega, which is 62.83. We know theta, 45 degrees. And we know n, which is equals to 4. So let us substitute the values and find out the answer. So omega PC is equals to 62.83 into cos of 45 divided by 4. We get 11.068 radian per second. So angular velocity of connecting rod is 11.068 radian per second. Numerical number 3. In a slider crank mechanism, the stroke of the slider is 200 millimeters. Obliquity ratio is 4. The crank rotates uniformly at 360 rpm. While the crank is approaching the IDC position, we have to determine the velocity and acceleration of piston. The stroke of the slider is given as 200 millimeters. So from this stroke we can determine the crank radius using this equation, s equals to twice r. So stroke is 200, which is equals to 2 times the crank length. So crank length is 100 millimeters. Next, obliquity ratio is 4. So n is equals to L by R, which is equals to 4. We have determined R, which is 100. So from this we get the value of L, which is equals to 400 millimeters, length of the connecting rod. Now the crank speed is 360 rpm, which is equals to 37.699 radian per second. Now this is the condition of problem. The crank is approaching the IDC. So for this we take theta equals to 0 degrees, because we always measure theta from IDC. Since the crank is approaching IDC, theta becomes 0. So under these situations we have to find out the velocity and acceleration of piston. Velocity of piston can be determined using this equation. So let us substitute the values. R is 0.1 meters, length of crank. Omega is 37.699. Theta is 0, and n is 4. So sine of 0 is 0. Sine of twice 0 is 0. So 0 into this 37 is 0. So velocity of piston is 0. Now for acceleration of piston we have this equation, F equals to r omega square cos of theta plus cos twice theta upon n. Let us substitute the values. R is 0.1 meters. Omega is 37.699 radian per second. Theta is 0 and n is 4. So after solving this we get acceleration of piston as 177.65 meter per second square. Numerical number 4. In an IC engine mechanism has a crank of 10 cm long and connecting rod of 40 cm long. The crank is rotating at 10 radian per second clockwise. At a particular instant, the crank is inclined to IDC at 30 degrees. For this position of the mechanism, what is the velocity of piston? Now, crank length, we indicate crank length by R. So crank length is 10 centimeters. So R equals to 10 centimeters. Connecting rod is 40 centimeters long. So L equals to 40 centimeters. And from the values of L and R, we have to determine the obliquity ratio N, which is equals to 40 divided by 10 is 4. Now angular speed of the crank is 10 radian per second clockwise. So omega equals to 10 radian per second. At a particular instant, the crank is inclined to IDC at 30 degrees. So theta with respect to IDC is 30 degrees. For this position of the mechanism, what is the velocity of piston? This is very simple numerical. So we'll find out N, which is L divided by R. 40 divided by 10 is 4. We'll substitute the values in the equation of Vp, which will give velocity of piston. R is 0.1 meters, 10 centimeters, 0.1 meters. Omega is 10 radian per second. Omega is 10 radian per second. Theta is 30 degrees with respect to IDC, and N is 4. So we get velocity of piston as 0.608 meter per second. So this was a pretty simple numerical. Now example number 5. An IC engine runs at 600 rpm. Length of connecting rod is 240 millimeters. and obliquity ratio is 4. Linear velocity and acceleration of piston at 40 degrees of the outstroke. We have to determine the linear velocity and linear acceleration of piston at 40 degrees of the outstroke. So length of connecting rod is 240 millimeters. Obliquity ratio is given as 4. So we have n equals to 4, L equals to 240. So we can determine R. So R is 60 millimeters. Engine speed is 1600 rpm. So in radian per second, omega equals to 167.559 radian per second. Now the stroke length is 2 times the crank length. So this is equals to 120 millimeters because crank length is 60 mm. So stroke becomes 120 millimeters. Now the condition of problem is piston displacement is 40% of the outstroke. Outstroke and instroke both are the same length, both are of the same length, which is 120 millimeters. And the piston displacement xp is 40% of the outstroke s. So which is equals to zero point 0.4 into 120 millimeters is the piston displacement. So xp is 48 millimeters. So piston displacement is 40% of the outstroke. So 0.4 into 120 gives 48 millimeters is the instantaneous displacement of piston. Now for this displacement of piston, we will determine the angular displacement of crank, which can be obtained using this equation. So we'll substitute the values. Xp is 48, R is 60, R is 60, obliquity ratio N is 4. By substituting all these values in this equation, we can determine the value of theta, which is 71.68 degrees. So when the piston has traveled 40% of the outstroke length, the corresponding displacement of crank is 71.68 degrees. Now we will use this value of theta to find out the linear velocity and acceleration of piston. So now we have n equals to 4, r equals to 60, omega equals to 167, and theta is equals to 71.68 degrees. So velocity of piston is equals to, by substituting these above values in this equation, r is 0.06 meters, omega is 167, theta is 71.68, and n is 4, so twice n is 8. So we get velocity of piston as 10.3 meter per second. Now for acceleration of piston, we'll substitute these values in this equation so that we get Fp equals to 191.55 meter per second square. Now example number 6. The stroke of steam engine is 15 centimeters and the connecting rod is 30 centimeter in length. The crank rotates at 600 rpm. While the crank is made the angle of 45 degrees with respect to IDC, we have to determine angular acceleration of connecting rod. Now the given data, stroke length is 15 centimeters, which is equals to 2 times the crank length. So from this, stroke is 15 centimeters, we can find out the crank length R, which is 7.5 centimeters. Connecting rod is 30 centimeters in length, so L equals to 30 centimeters. Now from L and R, we can find out obliquity ratio N, which is equals to L by R. So 30 divided by 7.5 is 4. So we get obliquity ratio as 4. Crank speed is 600 rpm. So in radian per second, crank speed omega is 62.83. Crank angle is 45 degrees from IDC. We have to determine angular acceleration of connecting rod, which can be determined using this equation. Alpha PC, angular acceleration of connecting rod, is equals to minus omega square into sine of theta divided by n, where omega is the crank speed, theta is the crank angle with respect to IDC, and n is the obliquity ratio. So let us substitute the values. Omega is 62.83, theta is 45 degrees, and n is 4. So we get alpha PC is equals to minus 697.8 radian per second square. Angular acceleration of connecting rod. Example number 7, a slider crank mechanism with zero offset, means this is inline slider crank chain, has the crank and connecting rod length equals to 30 centimeter and 30 millimeter and 150 millimeters respectively. The crank rotates at 600 rpm in clockwise direction, and the acceleration of slider then the acceleration of slider in its extreme position is. So we have to determine the acceleration of slider in its extreme position. That is, when the slider is at TDC and when the slider is at BDC, we have to determine its acceleration. So R is 30 mm, length of crank, L is 150 millimeters, length of connecting rod. So obliquity ratio N equals to L by R, 150 divided by 30, N is 5. Crank speed is 600 rpm. So crank speed in radian per second is omega equals to 2 pi n by 60 is 62.83 radian per second. Now the problem condition is the piston is at its extreme positions. So when the piston is at its extreme position, crank angle will be 0 degrees when the piston is at TDC, and the crank angle will be 180 degrees when the piston is at BDC. Because when the piston is at TDC, crank pin will be at IDC. So crank angle will become 0 degrees, and when the piston is at BDC, crank pin will be at ODC. So the angle with respect to IDC is 180 degrees. So for these values of theta, we have to determine the acceleration of slider, which is given by this equation: Fp equals to r omega square cos of theta plus cos twice theta upon n. So for the first condition, when the piston is at top dead center, theta is 0 degrees with respect to IDC. We'll substitute the values. R is 0.03 meters, L is 62. Omega is 62.83, theta is 0 degrees, and n is 5. So we get acceleration of piston as 142.11 meter per second square. 142.11 meter per second square is the acceleration of piston when it is at top dead center. Now for second case, when the piston is at bottom dead center, crank angle with respect to IDC is 180 degrees. So after substituting the values, we get acceleration of piston as minus 94.74 meter per second square. Now question number 8. A reciprocating engine has a crank of 60 millimeters and a connecting rod of 240 millimeters. The crank speed is 1200 rpm. What is the maximum velocity of piston? Crank length R is 60 mm. Connecting rod length L equals to 240 mm. So obliquity ratio N equals to L by R equals to 240 divided by 60 is 4. Speed of crank is 1200 rpm. So speed in rpm, radian per second, is 125.66. Now we have to find out maximum velocity of piston. The velocity of piston is maximum when its acceleration is 0. So we'll find out the crank displacement theta for maximum velocity of piston using this equation. For maximum velocity, Fp equals to 0. So by substituting the values of R as 0.06, omega as 125, and N as 4, we'll solve this equation to get the value of theta. So we'll solve this equation. This equation is quadratic equation in cos of theta. So after solving, we get theta equals to 77.01 degrees. So this theta corresponds to the maximum velocity of piston, or when the acceleration of piston is 0. So for maximum velocity, crank displacement is 77.01 degrees. Now the velocity of piston corresponding to this position of the crank is equals to V P equals to R omega sin of theta plus sin twice theta upon twice n. We'll substitute the value of theta as 77.01 in this equation to get the maximum velocity of piston. So we get maximum velocity of piston as 7.758 meter per second. Example 9. Crank radius and connecting rod length for an IC engine mechanism are 10 centimeters and 40 centimeters respectively. The crank is rotating uniformly at 1050 rpm clockwise. Using analytical method, find out the acceleration of piston as well as the angular acceleration of connecting rod when the crank is at 20 degrees past the bottom dead center. Now crank length is 10 centimeters. So R is 10 centimeters. Connecting rod length is 40 centimeters. So L equals to 40 centimeter. Crank speed is 1050 rpm. So from the values of L and R, we will determine N, which is equals to 40 divided by 10 is 4. So crank speed is 1050 rpm clockwise. So in radian per second, omega equals to 2 pi n upon 16, which gives omega as 109.95 radian per second. Now we have to determine the acceleration of piston as well as angular acceleration of connecting rod under this condition. That is when the crank is at 20 degree past the BDC. So let us take reference of this configuration diagram. We always measure theta with respect to IDC. Now the crank displacement is given from bottom dead center as 20 degrees and the crank is rotating in clockwise direction. So let us suppose that it is given that crank is rotating in clockwise direction, so crank will move like this, and at the instance the displacement of crank is 20 degrees from IDC. We measure theta 20 degrees from BDC, so we want theta from IDC, so theta from IDC becomes 180 plus 20, so theta with respect to IDC is 200 degrees. So we'll make use of this value to solve the equations for piston acceleration and angular acceleration of connecting rod. For piston acceleration, Fp equals to R omega square cos of theta plus cos twice theta upon n. So after substituting the values, R equals to 0.1 meters, omega is 109, theta is 200, and obligatory ratio is 4. We get acceleration of piston as minus 904.48 meter per second square. The next, the angular acceleration of connecting rod, which is determined using this equation. Alpha PC is equals to minus omega square, where omega is crank speed, sine of theta, where theta is crank displacement, and upon n. N is obligatory ratio. Now, after substituting the values, we get the angular acceleration of connecting rod as minus 1033.67 radian per second square. Now, question number 10. In a slider crank mechanism, the stroke of slider is 200 millimeters, obligatory ratio is 4, crank speed is 360, and the condition of problem is that crank is perpendicular to the connecting rod. Under this condition, we have to determine velocity and acceleration of piston. Now, stroke length is given as 200 millimeters, which is equals to 2 times the crank length. So 200 equals to 2 into R. So we get crank length R equals to 100 millimeters. Obligatory ratio is 4. So N is equals to 4, which is equals to L by R. So from this, we get the value of length of connecting rod L, which is 400 millimeters. The crank speed is 360 rpm. So crank speed in radian per second is omega equals to 2 pi n upon 60, which gives 37.699 radian per second. Now the condition of problem is that crank is perpendicular to the connecting rod. So the configuration diagram is like this. Crank R is perpendicular to connecting rod L. So angle between the L and R is 90 degrees. So we get tan of theta equals to L upon R, opposite side upon adjacent side, which is equals to N. So tan of theta equals to N. We have N is 4, so tan of theta is 4, theta is tan inverse 4, which is 75.96 degrees. So we have utilized the problem condition to determine the instantaneous displacement of crank theta with respect to IDC. The condition of problem was crank is perpendicular to the connecting rod. So from this we get right angle triangle, and from this right angle triangle we have obtained the value of crank displacement theta with respect to IDC. Now R is 100 mm, omega is 37, theta is 75, which we have obtained. N is 4. So velocity of piston is R omega sine of theta plus sine twice theta upon n. We'll substitute the values. R is 0.1, omega is 37, theta is 75.96 for the instant when the crank is perpendicular to connecting rod, and n is 4, so twice n is 8. So we get velocity of piston as 3.87 meter per second. And number 2, acceleration of piston r omega square cos of theta plus cos twice theta upon n. So we have all the values. We have r, which is equals to 0.1, omega 37.69, theta 75, and n is 4. So after calculating this, we get acceleration of piston as 3.13 meter per second square. Thank you.